very nice welcome to the Bhartiya Kisan, Quantum Farmer, Quantum Krisaks, a quantum physics by this Quantum Kisan, Quantum Krisak and Quantum Farmer. And today's topics is on the uncertainty principle. The uncertainty principle. So, a great scientist, Heisenberg, born in 1901 and remained till 1976, was a German theoretical physicist. He was one of the founder of quantum mechanics and received the Nobel Prize in 1932. So let's discuss the uncertainty principle given by Heisenberg. Heisenberg discovered that the product of the position and momentum uncertainties of a quantum jet, such as the wave packet, is greater than or equal to Planck's constant h. Thus, according to Heisenberg uncertainty principle, delta x into delta p sub x greater than equal to h cut. This is equation 1, where h cut is h by 2 pi, and here delta x and delta p sub x, delta x and delta p sub x are the uncertainties in the x component of the position and momentum of a microscopic particle, respectively. Similar relationship holds for the y and z components of the position with their respective momenta of the object. However, you should note that the Heisenberg uncertainty principle does not impose restriction on the simultaneous and precise measurement of x, y and p sub z, or y, p sub x and p sub z etc. The restrictions are only on what called as conjugate variables, that is for x along x comma p sub x, along y, y comma p sub y, and along z, z comma p sub z. Thus we have delta y into delta p sub y greater than equal to h cut. This is equation 2, and delta z into delta p sub z greater than equal to h cut, and similarly delta r into delta p sub r greater than equal to h cut, sub for subscript. So a general statement of Heisenberg uncertainty principle can be given as the value of two canonically conjugate variables cannot be simultaneously measured with infinite accuracy, that is with zero error, for a microscopic particle. The product of uncertainties in the simultaneous measurement of conjugate variables always has a value above a certain minimum, which is approximately equal to the Planck's constant. So this is the statement of uncertainty principle. Now we should note that the uncertainty relation delta x into delta p sub x greater than h cut, or delta y into delta p sub y greater than equal to h cut, has been obtained purely as a mathematical property of a wave packet. Hence, this relation is a fundamental as wave-particle duality. Like wave-particle duality, the uncertainty principle, though inversely applicable, is of significance only for microscopic system. Now, according to equation 1, for a microscopic system, there cannot be a state in which p sub x as well as x have a definite values. We can never simultaneously uncertain values of both position and momentum with arbitrary accuracy. If the position of the microscopic particle is defined, that is measured precisely, then the uncertainty in its momentum will be infinite. That is, we will not have any idea of what is momentum is. Similarly, if we are able to precisely measure the particle's momentum, we will have no knowledge of its position. Thus, for instance, in quantum mechanics, a microscopic particle's motion cannot be described by an equation like x equal to a sine omega t, because it implies definite velocity at a definite position. In other words, in other words, the uncertainty principle does not allow the concept of a trajectory. Thus, unlike classical physics, a definite path of a microscopic particle with definite velocity at every point on the path is not possible in quantum mechanics. So, we will take up this point once again. Another form of uncertainty principle finds use in atomic processes. Sometimes we might wish to measure the energy emitted in an atomic process in a time interval del t, then we require an uncertainty relation between energy and time. For this, we write m into delta x by p into delta p by m greater than equal to h cut. This the first factor delta x by v or delta t and since E equals to P square by 2m and delta E equals to P into delta P by m, we get delta E into delta T greater than equal to H cut. And this is equation 5 for B. This relation shows in the uncertainty in energy and time. Here delta T represent uncertainty in time and delta E represent uncertainty in energy. So equation 5 and 6 where delta is uncertain in time, here delta t is the uncertainty in time localizability of the wave packet and delta is the uncertainty in its energy. A more precise calculation based on the nature of wave packet change this result to delta E into delta t greater than equal to h cut by 2. This is equation 6. Equation 5 and 6. Equation 5 and 6 tells us that in order for a microscopic particle to have a well defined energy state, the state must last for a very long time. It must be stationary. And if the energy state is short-lived, example, in the excited state of an atom, its energy is uncertain. This is revealed in the width of a spectral line. Suppose the excited atom having a lifetime of delta t makes a transition to a lower state, then according to equation 5, the energy or the frequency of the radiation radiation emitted by the atom is uncertain by an amount h cut by delta T. Thus, the radiation will not be chromatic as delta nu equals to delta E by h. It will contain frequencies between nu plus delta nu and nu minus delta nu, and the line with delta nu also known as natural width will be given by delta nu equals to 1 by 2 pi into delta T, equation 6. So let us consider an application of percentage principle. So here we are example to calculate the minimum uncertainty in the momentum of a He atom confined to a 0.40 nanometer region. So here is the solution. So see the solution. We know only that the He atom is somewhere in the 0.40 nanometer region. Therefore delta x 0.40 nanometer, and we know that from the equation delta p sub x greater than equal to h cut by delta x. So using the above equation equal sign, to obtain the minimum we have delta p sub x minimum equals to h cut by delta x using the given value 6.62 into 10 to the power minus 34 joule second divided by 2 pi into 0. Delta x value 0.40 into 10 to the power 9 meter. We gets the delta p sub x minimum as 2.64 into 10 to the power minus 25 kg meter per second. This example gives us a reasonable picture of what happens to He atom at low temperature if we try to make them stay in one region by solidifying helium. Even at temperature approaching absolute zero, the He atoms have considerably momentum. Even at temperature approaching absolute zero, the He atoms have considerable momentum since He atom has a mass of 6.7 into 10 to the power minus 27 kg. A momentum spread of 2.64 into 10 to the power minus 25 kg meter per second means that at some time the He atom probably has a momentum of at least that much, or a speed of at least given by v equals to delta p by m equals to 2.64 into 10 to the power minus 25 kg meter per second divided by 6.7 into 10 to the power minus 27 kg, which comes out to be 394 meter per second or 1400 kilometer per hour. So even when T, that is temperature, tends to 0 Kelvin, this large 0 point motion persists because of Heisenberg uncertainty principle. The associated kinetic energy is so large that He atom will not solidify even at T tends to 0 Kelvin unless more than 20 atmospheric of external pressure are applied. This pressure pushes the atoms close enough together so that their attractive binding forces will be large enough to hold crystal together.